Hey there! Welcome to this explainer. I'm absolutely pumped to have you here today because we're about to decode one of the most critical foundational pieces of the whole networking puzzle. We're talking about layer 4 of the OSI model. Yep, the transport layer. Look, whether you're grinding for your CCNA, diving headfirst into cybersecurity, or you're a developer or university student trying to really grasp how data actually moves across the internet, mastering this layer, it's an absolute game changer for sure.
To kick things off, let's just think about a totally relatable scenario. Picture your computer screen right this second. You might have a Zoom call open on one monitor, maybe a fast-paced multiplayer game running in the background, and I don't know, a massive file downloading in your browser. So, how exactly does your computer keep all of that perfectly separated without turning the data into a giant mess? Like, why doesn't a random chunk of your file download suddenly blast through your Zoom audio? Well, this whole explainer is really built around how the transport layer solves that exact puzzle seamlessly, literally millions of times a second.
Okay, let's dive right into this. Here's a quick look at the game plan for today. We're going to decode the transport layer, pit TCP against UDP, break down the three-way handshake, explain ports and sockets, and then explore flow and congestion control. And finally, we'll wrap up with some rapid-fire, practical exam scenarios to really test what you've learned.
All right, starting with Section 1, decoding the transport layer, or as I like to call it, the network's incredibly efficient shipping department.
So, sitting right there in the middle of the OSI stack, snug between the session and network layers, is layer 4. It basically takes these massive chunks of data from your apps and preps them for their physical journey. You know, it doesn't build the network roads, and it doesn't write the digital letters themselves, but it acts exactly like a shipping department. It takes full responsibility for that end-to-end communication between the specific applications running on your devices.
Let's quickly hit its core duties. First up is segmentation. I mean, you obviously can't send a 20 megabyte file across the internet in one giant chunk, right? So layer 4 chops it up into nice, manageable pieces. Then, naturally, it handles reassembly at the destination, putting all those pieces back together in the exact right order. It also does error control, using clever little mechanisms like checksums to spot any corrupted data. Then there's flow control, making sure a super-fast sender doesn't completely overwhelm a slower receiver. And finally, multiplexing. This is the real magic. It's exactly how your computer can run Chrome, Discord, and Spotify all at the exact same time over just one internet connection.
Moving on to Section 2, TCP versus UDP. This is the epic battle of the internet's heavyweight protocols.
Now, this brilliantly illustrates the fundamental difference between these two. On one side, we've got TCP, the Transmission Control Protocol. I want you to think of TCP as a premium cargo delivery service, where the courier literally requires a signature for every single box. It's highly reliable, it completely guarantees ordered delivery, and it's connection-oriented. That just means it establishes a rock-solid connection before it even thinks about sending anything. The trade-off, though? Yeah, it's a bit slower. On the flip side, we have UDP, the User Datagram Protocol. UDP is way more like a live radio broadcast. It's incredibly fast, it's connectionless, but it offers absolutely zero delivery guarantees and no ordering. If a package drops in transit, UDP genuinely does not care. It just blindly keeps sending the next one.
So when exactly do we use TCP? Well, it's pretty much mandatory for applications where losing even a single byte of data would be an absolute disaster. When you're browsing the web using HTTP or HTTPS, transferring files via FTP, firing off an email through SMTP, or maybe accessing a secure terminal via SSH, you need TCP. Just imagine downloading an image and having random pixels missing, or worse, an encrypted text file showing up with missing characters. No way. TCP's error checking and retransmission processes ensure your file arrives flawlessly every single time.
By contrast, UDP is the undisputed king of real-time applications. We're talking live video streaming, fast-paced online multiplayer games, voice-over IP calls like your Discord or Zoom chats, and quick DNS queries. They all rely heavily on UDP. Think about it. In a voice call, if a tiny packet of data representing just a fraction of a second of audio gets lost, it's actually way better for the app to just skip it. You really don't want it pausing the entire conversation just to wait for that old audio to be resent. Speed and low latency are the absolute top priorities here, hands down.
All right, Section 3, the three-way handshake. Let's see exactly how TCP establishes trust before a single byte of data even moves.
Let's walk through how this builds step by step. Step 1, the client sends a SYN, or synchronized packet. It's essentially knocking on the door and saying to the server, "Hey there, I'd like to open a connection with you." Step 2, the server replies with a SYNAC, basically meaning,
Got it. I acknowledge your request, and I'm ready to synchronize too. Then, step 3, the client sends back a final ACK, or acknowledgement, saying, "Awesome, got your confirmation, let's start talking." It's honestly just a perfectly polite 3-step digital greeting that guarantees both devices are actually awake and ready to handle data.
Real quick, while we're on the topic of protocols, I really need to highlight a crucial piece of terminology. In Layer 4, when we're using TCP, the data units are specifically called segments. But when we're using UDP, those units are called datagrams. Guys, if you're taking a networking exam anytime soon, watch out for this trap. It is a classic trick professors love to use to catch you swapping the terms. Just file that little nugget away for later.
Okay, moving to Section 4, Ports and Sockets Explained. Let's dive into the exact mechanism that directs all this traffic.
I always like to think of your computer's IP address as the main street address of a giant apartment building. If that's true, then the port number is the specific apartment number inside. Make sense? So we've got well-known VIP ports from 0 to 1023, stuff like port 80 for regular HTTP and 443 for secure HTTPS. Then we have registered ports from 1024 to 49151, which are used for more specialized applications. And finally, the dynamic or ephemeral ports, running from 49152 all the way up to 65,535. Your computer actually just temporarily assigns these dynamic ports to itself whenever it's acting as a client connecting out to a server somewhere.
Now, when you smash that IP address and port number together, you get what's called a socket. So taking 192.168.1.5 and slapping a :80 at the end, that defines a totally unique connection endpoint. The IP gets the data to the right physical machine on the network, and then the port swoops in to deliver it to the exact application running on that machine. When you really step back and look at it, it's just an incredibly elegant system.
On to Section 5, Flow and Congestion Control. These are seriously the unsung heroes managing the entire internet speed.
So the really crucial point here is understanding the key difference between these two concepts. Flow control, that protects the receiving device. Let's say my super high-speed server is blasting data to your older, kind of clunky laptop. Flow control is what allows your laptop to literally tell my server, hey, slow down, so its buffers don't overflow. Congestion control, on the other hand, protects the network infrastructure itself. If the routers and switches out there in the middle of the internet are getting completely overwhelmed, TCP actually detects those drop packets and dials back the transmission speed to help clear out the traffic jam. TCP has a pretty brilliant toolkit to manage all this speed dynamically. For starters, it uses a sliding window mechanism to figure out exactly how much data it can send before it absolutely requires an ACK. It uses sequence numbers to make sure everything stays in perfect order. It even uses this really cool slow start algorithm, which does exactly what it sounds like. It begins sending data slowly, then ramps up the speed until it hits that sweet spot of maximum bandwidth the network can actually handle. Oh, and if an ACK doesn't show up before a timeout, yep, it automatically triggers a retransmission.
All right, Section 6, Solving Practical Exam Scenarios. We've covered the theory. So now I'm going to test you with the exact kinds of tricky questions a professor or a CCNA exam is absolutely going to throw your way. Let's see what you got.
Okay, here's a classic high-yield scenario. Why do fast-paced online multiplayer games exclusively use UDP instead of TCP? I want you to think back to what we just talked about regarding those trade-offs between speed and reliability. Take a quick second to lock in your answer.
Got it? Well, here's the breakdown. UDP prioritizes speed way above reliability. Think about a first-person shooter. If your character's position from half a second ago gets lost somewhere in the network, you definitely do not want the game to pause just to resend that outdated info. You just want the absolute newest position, and you want it as fast as possible. Waiting around for a TCP retransmission would just cause this intense, completely game-breaking lag. In this world, low latency absolutely trumps guaranteed delivery every single time.
All right, let's try a real-world troubleshooting question. If a user tells you they can't access a website, how do you troubleshoot the transport layer specifically? Like, how do you isolate layer 4 from all the other OSI layers?
So, to troubleshoot layer 4 like a pro network engineer, you'd check to see if port 80 for HTTP or port 443 for HTTPS is actually open and accepting connections. Look, if you can successfully ping the server's IP address, then you already know layer 3 is working just fine. But if that specific port is closed or maybe blocked by a firewall somewhere, then your transport layer communication just hard fails, and the website is never going to load.
I'm going to leave you with one final kind of provocative thought here. We know Layer 4 relies heavily on open ports and these very polite, structured handshakes, right? But what happens when malicious actors decide to exploit that politeness? What happens if a hacker spams millions of TCP SYN requests but intentionally never completes the final step of the handshake, basically leaving the server completely paralyzed just waiting for replies? Well, that's called a SYN flood attack, and it's a very classic transport layer vulnerability. Figuring out how network engineers actually defend against that, well, that pushes us right into the incredibly fascinating world of cybersecurity and the higher OSI layers. Anyway, I really hope this explainer completely demystified the transport layer for you today. Keep exploring, keep learning, and I will absolutely catch you in the next one.